let's just take a loaf of bread. Okay, you guys know what a loaf of bread looks like. I'm gonna attempt to draw a loaf of bread, but okay, so you've got some loaf of bread. So it's kind of like just this three-dimensional loaf, right? And I want to know what's the volume of the loaf of bread. And the way we can approach it is, well, I can take my loaf of bread and we can just slice it up, right? Slice it up into a bunch of slices. Okay, so okay, well, I'm not going to draw all the slices, but you imagine now each of these slices, each slice has a volume. So let's take, just maybe one representative slice of bread here. Maybe it looks like this. Okay, so we've got some loaf of bread and our slice of bread here. So it's got a certain thickness to it. So what's the volume of our slice? Well, the way we find it is we take the area of our slice, right? And then we multiply it by a certain thickness, right? The thickness of our slice. And that'll tell us roughly what the volume of our slice is. So it's the area times the thickness. Okay, so then the volume of our loaf of bread will just equal to the sum of the volume of our slices. And what that amounts to doing is just the sum of our area times the thickness. And in this case, well, if we're going to slice it into n slices of equal thickness, then we can use delta x as our thickness here. And the area here depends on its location somewhere along the x-axis. So now we're kind of placing this loaf here along an axis. And that's going to be essentially how we're going to approach the volume problem at first with this general slicing method. And here's another way to visualize it. We've got some 3D picture here, some 3D solid. And we're going to look at that solid as it extends along the x-axis here. At each point along the x-axis, we're going to slice the solid with a plane, and it's going to create a cross-section. So the area of a slice of our solid is called a cross-section. So here in this little plane that we slice it with, right, the intersection of that plane and our solid is what's called the cross-section. Okay, so at each point x along our axis, we have a cross-sectional area that goes with each point. And so we can take the volume of our kth slice, sort of like we were doing a moment ago. If I were to slice it up into n slices, equally spaced, so that they're all the same thickness, then the volume of my kth slice here would be approximately the area, the cross-sectional area of that slice times its thickness, right? So that's just the area times the thickness, like we were mentioning a moment ago. And that gives us a rough estimate of what the volume of that slice is. Notice it's not exactly, because we got sort of, we're assuming here it's just a flat slice, but it could have some edge or bevel to it around it. But if we do this with infinitely many slices, then it will begin to fill in all those edges and give us the exact area, or sorry, the exact volume. So we get the exact volume by taking the limit as the number of slices goes to infinity. So here you can picture it, right? The volume seems to smooth out as we increase the number of slices. As we do more and more slices, the volume will tend to approach the smooth volume that we have here. So by taking the limit as n goes to infinity of the sum of all our approximating slices, then it'll approach the integral from a to b of our cross-sectional area. Okay, so that'll be how we do the general slicing method, is we'll integrate from a to b the cross-sectional area. Okay, so that's what we're calling the general slicing method. Okay, so suppose I have a solid object which extends from x equals a to x equals b, and the cross-section of the solid perpendicular to the x-axis has an area given by a function a that is integrable on the interval ab, and the volume of the solid is just the integral from a to b of a of x. Okay, so we see that integrating here our cross-sectional area gives us the volume. Okay. So usually when we're using the slicing method, we need to think about this. What is our cross-sectional area? So if we're visualizing our solid, then we have to think about, okay, well, if it's some solid that extends along some axis from A to B, whatever that solid maybe looks like, it's got some slice here in the middle that has a certain cross-sectional area, whatever that area is. And whatever our shape is, some, some loaf-looking shape, I guess, whatever it looks like. So there's some A of x formula that tells me the area of each cross-section. Okay. Okay, so that's the trick, is trying to figure out what the area of our cross-sections are, and then we can integrate those areas to get the volume. So let's try and actually work through an example here. In this case, they're describing our solid in terms of its base and its cross section. So let's read it. It says, let R be the region in the first quadrant bounded by the coordinate axes in the curve y equals 1 minus x squared. A solid has a base R and cross sections through the solid perpendicular to the base and parallel to the y-axis are squares. Find the volume of the solid. Okay, so they're describing the base of our solid, which is this part of a parabola that's in the first quadrant. And then they're describing what the cross sections of our solid are because they're telling us that they're squares. So we're building a solid where the base is this parabola region, and building cross sections on top of that are just squares. So let's try and think about if we can visualize what this region looks like. So I'm going to draw out what our base looks like. And this is essentially, it's going to be like the footprint of our solid. In other words, it's like our solid is sitting on this base. So let's see. So it's in the first quadrant and it's bounded by y equals 1 minus x squared in the coordinate axes. So oops. So it's like this part of a parabola. So I think it would look like this, right? Goes through these points here at 1, 0 and 0, 1. So it's like our upside down parabola. So this is, again, this is like the footprint of our solid. So our solid is going to be built on top of this base. And they tell us that the cross sections here are going to be running parallel to the base and perpendicular, I'm sorry, parallel to the y-axis and perpendicular to the base. So the idea here is our cross sections are going to be built on top of it. Imagine now this would be where one of my slices would go here at some point that's, let's call it X. This is where my cross section would go. And let's see, what would that cross section look like? Well, in this case, we're given our cross sections are squares. And the idea is that the length of the base of our square, we imagine here this one of the sides of our squares is going to lay along this line here, but kind of sticking out of the plane a little bit. So sticking out of the screen. If you can imagine here, the square coming out of the screen. All right, that would be our cross section right there. Okay, and the area of that cross section is just the area of this square, right? It's just a square where the sides are of length y, where y is given by this equation y equals 1 minus x squared. So that tells us the length of the sides of our square. Okay, so that's, if we do that at every point along here from one end to the other, we get basically all the slices going from x equals 0 to x equals 1 will form our solid. Okay, so again, here I'm trying to help you guys visualize how this solid is formed, but there's these two pieces that we're putting together. We've got the cross sections that are being placed on top of our base. Okay. So again, the base here is like the bottom of our solid. And then the slices are these squares that are sticking out of the base. Okay, so you can imagine it at each point along here, there's going to be these different slices, okay? And that all comes together to form this three-dimensional solid. And let's think about now what the area of our cross sections are. So here it's actually easy enough to find the area of a square. If we know that the sides are length y, right? They're both y along each side. Area would just be y squared, and in this case, y is given by the equation 1 minus x squared. Okay, so that's our cross-sectional area as a function of x. 1 minus x squared squared. Okay, so that gives us the area of our cross-section. So then to get the volume of our solid, right, we're just going to integrate the area of our cross-section. And in this case, our cross-sections run from 0 to 1 along the x-axis. So it's just a matter of now integrating from 0 to 1, 1 minus x squared squared. And here I'll go ahead and FOIL this out. And then find the antiderivative. So we get x minus 2x cubed over 3 plus x to the 5th over 5 when we find the antiderivative, and then evaluate from 0 to 1. So plugging in 1 for x, we get 1 minus 2 over 3 plus 1 over 5, and then evaluating it at 0, just be 0. So then let's see, combining this stuff, we get, see, 1 minus 2 over 3 is 1 over 3 plus 1 over 5. Let's see, so that would be 8 over 15. Okay. So actually working out the integral here isn't so bad, but the trick is trying to visualize or see how the solid is formed with the description that they're giving us about each of these two pieces. They tell us how the base of our solid looks and what the cross sections are. Of course, my picture here is a little bit hard to see exactly what this solid looks like, but there's a good picture in the book here that we can look at. Here's again sort of another way to visualize it. We've got our base here. Was this portion of the parabola in the first quadrant, and we're building on top of that our solid with, here's one representative slice, one cross section of our solid. So doing that along each different x value along the x-axis gives us this three-dimensional solid here. Okay. So yeah, I'm not always great at drawing these three-dimensional pictures like we see here, But notice I didn't really need this perfect 3D picture to be able to put the pieces together. All I needed was how to visualize the base and how to visualize the cross sections, and then putting those two pieces together to form the area of our cross section along each different point on the x-axis. Okay. But yeah, it helps to kind of be able to visualize this, maybe mentally at least, how the solid is formed. Here's another example. Suppose we have a solid that has a base that is bounded by the curves y equals x squared and y equals 2 minus x squared in the xy plane. Cross sections through the solid perpendicular to the base and parallel to the y-axis are semicircular disks. Okay, so if we want to find the volume of this solid, let's do the same thing that we did a moment ago. Let's try and visualize what are the two pieces that they're describing here. The base is a region that's bounded between the curves y equals x squared and y equals 2 minus x squared. So let's see if we can sketch out roughly what our base looks like. So we got y equals x squared is one boundary of our base here. And then y equals 2 minus x squared. So now just the flipped over version of this and then shift it up 2 units. Get the other boundary of our base. And we can sort of see that our base here is in between these two curves, where we can take a moment here to see that the curves will intersect at these points here. You can solve it out here by equaling them to each other. You get 2x squared equals 2. So x squared equals 1, and that gives me x equals plus or minus the square root of 1, which is just 1. So we see they intersect here at -1 and +1. So that gives us the boundaries of our region. And they're describing the cross sections here that are going to lie on top of this base that run parallel to the y-axis, and they're semicircular disks now. Okay, so they're not squares anymore, but they're semicircular disks. So you can imagine that the base of our disk, if I were to lay the disk here along this segment, would stick out of the board a little bit. It would be a semicircular disk, and so you can do that at each little slice along the base here. So let's try and visualize our cross sections now. Since here I can just pull this cross section over here, and let's look at it. Here, I'll just kind of flatten it out like this. It's a semicircular disc. So it's a half of a circle, where the diameter of our base of this semicircle lies along this segment here, going from 2 minus x squared on the bottom to x squared on the top. So the length of that little piece here would be x squared minus 2 minus x squared. So just think length of this segment would be subtracting the y coordinates at each point on the top and the bottom. Okay, so here's actually maybe I'll say it that way. First, we'll do, it's like I'm doing the top y top minus the y bottom to get the length of that segment, which is x squared minus 2 minus x squared. And that's going to be the diameter of this semicircular cross section. Combining it's just 2x squared minus 2. So that's the diameter. Of our semicircle. Okay. So then the question is, okay, if we want to find the area of this cross section, we probably should get the radius. So the radius would be our diameter divided by 2. So we'll do 2x squared minus 2 divided by 2. And so our radius here would just be x squared minus 1. That gives us the radius of our disk. And so then from there, we get the area of our cross section. Will be, well, it's a semicircle, so it's pi r squared over 2 because it's a semicircle. And because our radius here is given by x squared minus 1, we'll do pi times x squared minus 1 squared over 2. So why don't we now go ahead and integrate our cross sections to get the volume. In this case, notice our integral will go from -1 to +1. The boundaries of our region go from -1 to 1. And we got pi over 2 x squared minus 1 squared. And here I'll take the pi over 2 out first because that's just a constant multiple. I will FOIL out x squared minus 1 squared, so that'll be x to the 4th minus 2x squared plus 1. Now I will evaluate the antiderivative. We get x to the 5th over 5 minus 2x cubed over 3 plus x. Then we'll evaluate from -1 to 1. So evaluating it at 1, we get, let's see, we get 1 over 5 minus 2 over 3 plus 1. Minus evaluating it at -1, I think it just flips the sign. And so let's see. So I think here actually we get something similar to what we had before. This is 8/3, or no, sorry, 8/15. Plus another 8/15 gives me 16/15. Times pi/2, so I think it would be 8pi/15 when we combine it all together. Okay. So, oh, I noticed I actually did something a little bit off here, although it didn't make a difference in the end. Maybe you guys noticed here when I said top minus bottom here, I actually did it the other way around. Because here the top one isn't x squared, the top one is actually the one I wrote below here. The green one is the teal one is the one that's on top, which is 2 minus x squared. So yeah, technically that's a little bit off there. Should be careful. Here it didn't wind up making a difference though, so I just wanted to actually clean that up a little bit. And so over here, just give us something switched around a little bit. And we can see why that actually didn't make a difference in the end, because I wound up squaring it here. When I wound up squaring it at this step, it came out to be the same as if it were the other way around. So actually squaring it here came out to be the same. Okay. And again, here, let's try and look at some pictures that maybe show us. Can you guys try and visualize what this three-dimensional solid would look like? I mean, maybe it's hard to see with my picture here. We can imagine that this again, the base here is like this footprint of our solid. So that's where the solid sits on that base. And it's got these semicircular curves for the cross section. So maybe you can imagine it might look something like a dome or something, very circular looking. So if you imagine here, yeah, you can kind of see that it's got this sort of dome-shaped three-dimensional solid. Okay, so The next thing we're going to take a look at is extending on our basic idea here of finding the volume by slicing, where in the last two examples we were given how the solid is formed by describing exactly what its cross sections look like. The next thing I want to look at is forming a solid by taking a region and revolving it around an axis. So these are what are called solids of revolution. Okay, so take for instance a region that looks like this. So we've got the region R that's bounded between the curve y equals f of x and the x-axis on the interval AB. So we've got this region. Okay, so some two-dimensional region. So a solid of revolution is formed by revolving a region about an axis. So our goal here is to imagine the region R here. That's bounded by y equals f of x on the interval a to b and the x-axis. Is revolved around the x-axis. Okay, so here we're kind of indicating we're going to take this and we're going to revolve it around the x-axis. And so imagine that as we do that, this is going to sweep through some three-dimensional shape that's going to form our solid of revolution. So here, let's kind of look at another picture to see how that solid is formed. All right, we've got our three-dimensional, our two-dimensional region R. And we sweep through this portion of the, we form the solid by sweeping around the x-axis. So we imagine the region R is rotated around the x-axis to form this three-dimensional solid like we see here. Okay, and the way that we want to approach this is we can imagine that the solid that's formed here has cross sections that are disks. They're circles, right? So to take the final picture that we have here, if I were to slice it at some point, I slice it at some point x along the x-axis, and we look at the cross section, it's just going to be a circular cross section. Okay. So the cross sections of our solid revolution are always going to be circles, disks. And so finding the volume of our solid that's formed here is a matter of integrating these disks, or the area of these cross-sectional disks. And notice here that the height of our curve here, if I were to look at the original f of x graph, the height of the curve there gives us the radius of our disk. So that's our y equals f of x, will give us the radius of our disk that's used to form our solid. So they're circular disks, and so the area of our cross section are going to be the area of these disks, where the radius is y equals f of x. And so in this case, at least in this example here, we can then compute the volume of our solid by doing the integral from a to b, pi times f of x squared. Okay, so computing the volume using these cross-sectional disks is called the disk method. Okay. Here's the same picture. We've got this cross-section that's a circle. It's a disk. We know the area is pi f of x squared. And so integrating that, we get the disk method here. So let f be continuous. And f of x is greater than or equal to 0 on the interval ab. If the region R bounded by the graph of f, the x-axis and the lines x equals a and x equals b is revolved about the x-axis, the volume of the resulting solid of revolution is integral from a to b of pi f of x squared dx. Okay, and again here we are assuming that in this case we're revolving about the x-axis, right? So okay, whatever our solid looks like, it's formed by taking this curve f of x and revolving about the x-axis. We see that the cross sections here are disks. Okay, so let's practice this a little bit. Let R be the region bounded by the curve, f of x equals x plus 1 squared, the x-axis, and the lines x equals 0 and x equals 2. Find the volume of the solid of revolution obtained by revolving R about the x-axis. Okay, well let's try and picture the region that we're dealing with. So it's going to be like part of a parabola, right? X plus 1 squared is a parabola shifted to the left by 1 unit. So I think we can see that here it would pass through 0, 1 there when x is 0. And then when x is 2, we get, let's see, 3 squared is 9, so something up here. Okay, so this is our little region that we're dealing with here. And we're going to form our solid just by taking this region and revolving it around the x-axis. Okay, so we can imagine that it's just going to form kind of like almost like a horn or some sort of maybe funnel-shaped graph. And of course here, right, we're just going to use the disk method. Say we choose a random cross-section there in the middle, will be a disk where the radius is r f of x. Okay, so here our volume will be integral from 0 to 2 pi times f of x squared. So again, it's just using the disk method here. And let's see, so we got pi times f of x is x plus 1 squared. So x plus 1 squared squared will be x plus 1 to the 4th. Okay. Nice thing is that I don't need to FOIL this out with the power of 4 to integrate it. It's a simple x plus 1 factor in there. So I can do a substitution. You might even be able to do this mentally if you're comfortable with substituting it. But yeah, you can just let u equal to x plus 1. And so that's a nice simple substitution where du is equal to dx. So the integral is just u to the 4th du, much simpler integral. I don't have to deal with foiling it at all. Our limits of integration would change from from 1 to 3. So then when we integrate, we get u to the 5th over 5. Evaluate from 1 to 3. So I get 3 to the power of 5 over 5 minus 1 to the power of 5 over 5. Let me see. So 3 to the power of 5, what is that? I think that would be 243. So we would have 242 over 5. Okay, so yeah, you can leave your answer like that, of course. Just leave it in terms of pi. And yeah, here's again the picture. You got the region R, and the radius of our disk would be represented by that little line segment that we draw there. By the way, I tend to like to draw the little line here. This is a good habit when we're doing these so that we can see how the disks are formed, or maybe we'll have some other thing that we have to visualize. But here, notice I kind of naturally always do that. I just will always draw the representative line here and then imagine how the disk is formed to represent the cross section. Just a general best way to approach it is to try and visualize how your cross sections are formed. Okay, so here we see that y equals f of x gives me the radius of my disk. Okay, just like we see here. And there we have our sort of horn-shaped solid, right? Alrighty. Do you guys have any questions so far?
I guess not.
All right. So maybe here I'll just introduce the washer method, which is kind of extending on the idea of the disk method, but now we're imagining now there's like a hole in our disk. So now it's like our solid is formed when we have this region that's got a gap between the region and the axis of rotation. So when I revolve this region around the x-axis, there's going to be a gap that's formed in our solid. So here that you notice that the cross sections will not be perfect circles. They'll actually be washers, right? So there'll be circles with holes in the middle. Okay. So the washer method is just a variation of the disk method with a hole in the middle. Okay. So to find the area of our washer, well, we take the outer radius minus the inner radius. Sorry, I should say that the other way around. So it's the area of the outer circle minus the area of the inner circle. So it's pi times the outer radius squared minus pi times the inner radius squared. Okay. So it's always important to kind of identify what the outer radius and what the inner radius is. So then once we have that, then we can see our cross-sectional area would be pi times f of x squared minus pi times g of x squared, where f of x is the outer function, g of x is the inner function. So that gives me the cross-sectional area here is pi f of x squared minus g of x squared. Okay, so this is what we're going to think of with the washer method. We've got the outer radius and the inner radius are the outer function and the inner function. Okay. But here, maybe we can just set this one up and then we'll finish it up next time. So it says, the region R is bounded by the graphs of f of x equals the square root of x and g of x equals x squared between 0 and 1, what is the volume of the solid that results when r is revolved about the x-axis? So I'm going to just sketch these out real quick and then we can leave it there. But you've got the square root of x graph, looks like this. And then you've got the x squared graph, looks like this. And so when we revolve this region about the x-axis, you can imagine here that if I draw this little strip, that's going to form the inner radius there with the bottom graph, and then the outer radius with the upper graph. So then our volume, the integral from 0 to 1, right where they intersect here. Pi times the outer radius, which is the square root of x, minus the inner radius, which is x squared. Okay, so I'm going to just leave it set up like that, and we can come back to this example next time.